This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So that's an important insight. To understand possible flows, we'll consider stationary waves in a supersonic flow. So what I'm going to do today is going to build on things that I've done in the past, and I'm going to do oblique shocks. And oblique shocks have the property that we can, it's okay, I've only just started. Oblique shocks have the property that there's a line in the fluid or a particular path, characteristic in the fluid, across which the Mach number changes discontinuously. And that idea is a method of characteristics for steady supersonic flow, which I'm not going to do, but I'm going to explore and use some of those ideas. So let's start first with an oblique shock wave. And so we're going to suppose that we're going to add a uniform velocity v. We're going to superpose that on the flow field of a normal shock wave. So here's the normal shock wave, comes in here with a velocity just greater than the speed of sound, and the velocity leaving behind the shock we saw was subsonic. So it had a lower velocity than the velocity coming in. And we're now going to add a velocity that's perpendicular to this velocity of magnitude v. So it's as if we are a convective observer moving with respect to a point in the flow. We're going to move down, and it's as if the flow is moving up. So we're going to add a v component of velocity. And we're going to look at conservation of mass. Now, in the conservation of mass, you'll have a mass flux across this surface of minus rho 1 u1 and out of rho 2 u2. So that was our conservation of mass that we've had before. And we had the force in the x direction will be the net flux of momentum out. So that'll be rho 2 u2 times u2 out, and the flux out on this surface here will be minus rho u1 squared, minus because u dot n is minus. And the force in this direction is P1 times unit area minus P2. At the same time, if we had a control volume that looked like this, we could see that we have a flux of mass across this face. We have uniform flux of mass across this face and across this face. So nothing happens there. But we could have a flux of momentum. There would be a flux of momentum out across this face, which would be minus rho 1 u1 v. And there would be a flux of momentum across this face here, which would be a rho 2 u2 v, the mass flux times v. And you can see that that's the same thing as this equation, so nothing's happened. And for my energy equation, it's a steady flow. So I have only to add to the kinetic energy. I have an H1 here and an H2 here. There's no rate of change of energy in the volume, and so I have a mass flux of minus rho 1 u1, H1 plus a half u1 squared plus a half v squared, which is the kinetic energy in this direction. And coming out of it, I have H2 plus a half u2 squared plus a half v squared coming out. And you can see that the v squared, because rho u1 and rho u2 are equal, it cancels. So there's no net transverse flux of mass, momentum, or energy out of the volume, which includes the shock. So that's an important idea. We can, and you would have expected it, we can add a Galilean velocity field and nothing will change. Nothing changes. So
Gary, what's a Galilean velocity field again?
a Galilean velocity field is a Galilean transformation is that you move at constant velocity. So if you wanted to know something about the force on this object as I move it, that won't change if I move with respect to this. If this is, now if I accelerate with respect to this, it'll change. But if I move at constant velocity, it doesn't affect the force or the acceleration. And so I can always add a uniform velocity to any dynamics. I can add a uniform velocity, and if the problem is a steady problem, not changing with time, then it won't make any difference.
So any frame of reference where Newton's second law will be preserved?
Yes, yes, yes.
As if it were accelerating?
If it were accelerating, it's problematic.
Yep, yep.
You'll have rates of change and momentum in the volume and so on and so forth. So, and that is called a Galilean transformation, after Galileo, of course. All right. So now another way to look at this figure is to see that I could, in fact, because I can add this velocity to this velocity, I have a new velocity, which is w, in this direction. And then the shock wave is oblique to this velocity. It's only the normal velocity that's going to count. It's only the normal velocity that's going to be the Mach number, the normal Mach number coming into the shock wave. The transverse velocity doesn't have any effect at all. So I can always use the normal Mach number to work out what's going to happen across this shock. So that's a very important idea. And you can see that if U1 is greater than U2, it must be, then, and I have the same V, then this angle has turned. The flow will have turned through an angle theta, because V over U2 is the tan of this angle. And this angle here is the same as this angle here. We have beta here, so this is 90 minus beta there. So, so I can redraw that figure, and I want to redraw it so that it's more physically comprehensible. So here's the normal velocity, u1, and here's my added v component of velocity. So then the resultant velocity field is w1, but it's at now an oblique angle to this shock wave, and coming out of it is the normal velocity u2 plus the transverse velocity v. And so the flow, which started in this direction, got turned to this direction because u2 is less than u1.
It might be a dumb question, but...
No, no question is dumb.
Oh, I can guess that, but
Forget that. You can ask anything you like.
say that the flow is supersonic, right?
And yes, and it is, for there to be a shock. So it's supersonic, W1 is supersonic, and U1 has got to be supersonic.
So beta will adjust in such a way that the normal component must remain supersonic. Otherwise, what I'm thinking is, what if it's very weakly supersonic, like 1.0, like
Yes.
a number of 1.01, and then it comes outcomes that are just
And it won't be turned. You won't be able to use the shock tube relations
right.
to get what I'm going to work out.
Okay, yeah.
So this only works if this is a discontinuity. And I've talked at some length about discontinuities. Discontinuity will satisfy the equations of motion. Not differentially, but integrally. Unless you know a lot about the stresses and the heat flux within the shock.
Yeah.
Now people do, but they didn't initially. All right. Okay, so beta becomes the angle of this flow now, W1, which is the sum of this flow field plus this velocity field. These two velocity components lead to this velocity. And now beta is the angle of the shock to the flow, and then theta is the angle through which the flow has to turn if this is a shock wave. And I think I now say, oh yes. So it's clear that beta is an angle whose tangent is u upon v. And since, and here's where I said what I said before, since u2 is always less than u1, the flow is always turned towards the shock. If this is a real shock, then the flow is always turned towards the shock. Okay. So now there is some algebra that's unfortunate in a way. We're going to define M1 as the total velocity W1 divided by A1. So since W1, I better go back to my figure. So W1 times the sine of beta is U1. So get that picture in your head. W1 times the sine of beta is U1. So now, or W1 times the sine of beta is U1, or U1 over W1 is the sine of beta. Therefore, U1 over A1 is W1, U1 over A1 is W1 over A1 sine of beta, and that's M1 sine of beta. So everything that you've seen me do previously for normal shocks, I'm now going to do for oblique shocks. So the normal Mach number, M1n, is U1 over A1, and U1 over A1 is M1 sine of beta. So the normal Mach number, M1n, is what I have to know, and that'll tell me what the pressure ratio is across the shock, what the density ratio is across the shock, and every other component across the shock. So the jump in static variables depends only on M1n. That is, on U1, which is W1 sine of beta. And in particular, the pressure jump, P2 minus P1 over P1, this is a formula that you might want to commit to memory. P2 minus P1 over P1 is 2 gamma over gamma plus 1, M1n squared minus 1. That's the normal shock Mach number coming into the shock. So there's a pressure rise when this is greater than 1. And that, of course, is going to be equal to 2 gamma over gamma plus 1 m1 squared sine squared beta, because m1n is m1 sine beta. So it's m1 squared sine squared beta minus 1. And rho 2 over rho 1, I worked that out for you before, and it was gamma plus 1 m1n squared over gamma minus 1 m1n squared plus 2. And the limit as the Mach number went to infinity was gamma plus 1 over gamma minus 1. That's the maximum density difference you could get across the shock. So we can rewrite that in terms of m1 and beta. So it's gamma plus 1 m1 squared sine squared beta over gamma minus 1 m1 squared sine squared beta plus 2. And etc. for T2 over T1, A2 over A1, and S2 minus S1 over R. So I could have worked those out if I wanted to. Now, evidently, beta, this angle of this oblique shock, it could be normal. And then I'd recover my normal shock wave. So the maximum value of beta is pi on 2, where it's a normal shock, for m1n greater than 1. Because, so, for m1n greater than 1, m1 sine beta has to be greater than 1. So sine beta has to be greater than 1 upon m1. And so we see something interesting here. We're going to define the Mach angle, mu, as an angle whose sine is 1 upon m1. So since m1 has got to be greater than 1, sine beta has got to be less than 1, and sine mu has got to be, if sine mu is equal to 1 upon m1, it means that beta has got to be greater than mu. So beta can vary. This oblique shock angle can vary between the Mach angle mu and pi on 2. And when beta is equal to mu here, then obviously m1n, which is m1 sine beta, is equal to 1. So now, so when beta is equal to mu, m1n is equal to 1. That is, for a weak shock, we can expect weak turning and theta to be small. And that's true for a weak shock. Now I want to, why is the Mach angle such an important idea? I want to motivate it. Supposing I was a sound source here, and I was propagating with this flow, with the speed W1, T1, and as I'm going along, I emit a sound wave. I have a pulse. It goes out. So that pulse, when I was here, would, if I'd started pulsing it here, then by the time I got to here, the pulse that I put out from here would have gone A1 times T, because this distance would have been W1 times T. And by the time I'm down to here, if this is T1, by the time I get down to here, I started here and I was pulsing this thing, and I got all the way down to here, and now the wave that I started to pulse could have only gone out a distance A times T1. So the Mach angle is this line here, which is tangential to every one of these sound waves that's been emitted. And so sort of physically you can see, well, the region out here will never know that there's a source that's been pulsing as I've been moving along. But everywhere inside that region, I'll know that there's been a sound source pulsing. So this is a quiet region out here, and it's not here. And so that's a Mach angle is a kind of angle of influence. And that's an important idea. The Mach angle is an important idea. And you can see that it corresponds with a line, and it's a path, and it's why the method of characteristics works so well in supersonic flow. All right. So I've said that sine mu is this distance here, which is AT1 over this distance here, which is W1 T1, and they cancel, and it's 1 upon the Mach number. Yes?
Along this path, A doesn't change?
A doesn't change.
A doesn't change.
No.
Only for this case, not for beta.
Well, for this case, this is the. These are weak. It's. I'm not producing strong shock waves. I'm just making them very tiny, weak waves. But I'm moving from this source here. I turned on my weak wave source at this point here, and I kept track of the wave front as I send out this pulse. So by the time I'm here, I send out the pulse, it will have traveled out to here. And then it will have traveled out to here by the time I'm down here. All right, so let's come back to this figure. So I want to work out something about beta and theta, or theta as a function of beta and M1, which is W1 over A1. So here's a picture of it. This is the oblique shock here. And here is the normal velocity coming into the shock and what leaves it. And here is the turning of the flow that's compatible with this velocity being less than this one. All right, so M2 here is W2 over A2 by definition. It's this velocity divided by the speed of sound. And U2 is therefore, U2 is W2 times the sine of this angle, beta minus theta. Because this angle here is beta, the flow got turned through theta because U2 is less than U1. And so this angle here, this whole angle from here to here is beta. So this angle here is beta minus theta. So U2, this velocity here, is W2 sine of beta minus theta. Now, downstream of this shock wave, this normal shock wave, M2n, which is this velocity U2, was given by 1 plus gamma minus 1 over 2 M1n squared over gamma M1n squared minus gamma minus 1 over 2. Or, and I wrote that down for you at the time, I don't remember it myself. So this is 2 plus gamma minus 1 M1n squared over, this becomes 1 minus gamma, and this becomes 2 gamma M1n squared. So this is an expression, and so now I can write an expression for M2n squared M2n is, by definition, U2 over A2. But U2 over A2, which is M2n, will be M2 W2 over A2 sine of beta minus theta. So now I can use that to find this theta and beta. So let's see how I'm going to do it. So m2n squared is m2 squared sine squared beta minus theta. So that I have that. And on the right-hand side, I have 2 plus gamma minus 1, m1 squared sine squared beta for this one by 2 gamma m1 squared sine squared beta plus 1 minus gamma. All right. So that says that if I knew theta as a function of m1 and beta, I could get m2. So if I knew beta and m1, and I knew what theta was as a function of m1 and beta, I could get m2. So that's a very basic idea, and I'm going to use it now. So how do I use it? Well, perhaps I've got to go back here to my figure. So U2 over V is the tan of beta minus theta, and U1 over the same V is the tan of beta. So how can I use that? Well, so U1 over V is tan of beta, and U2 over V was tan of beta minus theta. But U1 divided by U2, the V's will cancel. U1 will be tan of beta divided by tan of beta minus theta. But that will also be, from the conservation of mass, U1 over U2 will be rho 2. Rho 2 U2 is rho 1 U1. So that'll be rho 2 over rho 1. And I have an expression for rho 2 over rho 1 in terms of m1n squared. It's gamma plus 1 over 2 m1n squared plus 1 divided by 1 plus gamma minus 1 over 2 m1n squared. And so I can replace this.
That just comes from the previous normal shock relation.
That's just coming from the normal shock relation, and this ratio comes from the geometry.
Yep.
Right? So this says that the tan of beta minus theta I bring up here, and I bring this up over here, and this one down here, and I get, and I can write this m1n squared as m1 squared sine squared beta. So this m1n here in the top and bottom is m1n sine squared beta. And then, so this is all algebraically tedious, but the tan of beta minus theta is something that you all know. It's tan beta minus tan theta over 1 plus tan of beta plus tan theta. So you can put all of that in here, and you can finally get an expression for tan of theta. And I haven't put all the steps in because you've got to multiply this out and so on. But you can almost see how it goes. The tan of beta is therefore equal to this expression here. And if you want to see it derived in everlasting detail, you can go to Liebran and Roscoe, and it's equation 410. So this is a very important result. That's a general result. The flow will turn through an angle theta if m1 has some value and beta has some value. And beta is the angle between the flow and the shock, and m1 is the Mach number W1 over A. So you can use all of those normal shock relations to get this result. So this is a very important result. And I've just called it theta is a function of m1 and beta. And beta can be from beta equal to mu. Sine beta is therefore 1 upon the Mach number. And so that's when if I put sine beta equal to 1 upon the Mach number, I'll put it into here, and this 2 minus 2 gives me 0, so tan theta is equal to 0, so that's 0. Whereas for beta equal to pi on 2, beta, tan beta, has got to be infinity. Why do I say that? Because when tan beta is infinity when V goes to 0. So when V goes to 0, you'll get the normal shock again. So when V goes to 0, tan of beta goes to infinity. And so you get, if tan of beta is going to infinity, then this is also going to 0. So there are two places where theta is equal to 0. One when beta is pi on 2, and one when beta is mu. And this gives this wonderful figure of the turning angle as a function of beta. Here's beta is pi on 2, and beta can be between mu1 and pi on 2, where mu is 1 upon the an angle whose sine is 1 upon the Mach number. So only when m1 goes to infinity does mu go to 0, and you have this whole range here. Otherwise, you're from here to here. And a very important result from this figure is that you would expect that theta has some maximum value between when beta is between mu and pi on 2. If it's 0 here and 0 here, if theta is 0 here and 0 here, then it's telling you that there's going to be some maximum in between. Now that proved to be extremely significant. I was chatting, I used to play squash with Jerry Oestreicher, who was the chair of astrophysics at Princeton. And we were talking about astrophysical jets, astronomical jets. So you have this jet of fluid that appears to be coming out of the pole. And why on earth would there be a jet of fluid? And in fact, if you look at contours of radio brightness, you could see what looked like vortices. And you said, oh, good God, why are there, on this scale, when the mean free path was light years, why could you have something that looked vaguely like continuum fluid mechanics? Well, this astrophysical jet, if you take the contours of constant radio brightness and you presume a standard candle, which is the way astronomical distances are measured, you assume standard candles and the intensities falling off like 1 upon r squared. This object was 100, no, he showed me a scale that was, yes, the scale was less than half the length, significantly less than half the length of this object. And the scale was 150 kiloparsecs. And I said, what's a parsec? Knowing nothing about astrophysics. And he said, well, 1 parsec is 3 light years. So this object was 1 million light years long. And if you're not overwhelmed by that, you've got ice in your veins, to quote the chair of physics at Princeton. If you're not overwhelmed by it all, overawed by it all, you've got ice in your veins. So here's this object, and coming back to this, why does it happen? Well, if you have mass at infinity and you have a black hole, and the black hole has an extremely dense object, then it has very large gravitational force. And this mass at infinity will move towards the black hole. But what will happen to it as it moves towards the black hole? If it's in a sheet, and it could have some angular momentum, some tangential velocity with respect to the black hole. So you'll have to conserve angular momentum, but you'll also have the radial velocity, and the radial velocity will be changed by these laws. And conservation of angular momentum will mean that as this mass comes in, it'll spin faster and faster and faster until all the energy, all that gravitational energy it had at infinity is in the circumferential motion around the black hole. And it can't get any closer than that. And that radius is called the Schwarzschild radius, after the astrophysicist Schwarzschild who thought of it. So at the same time as the fluid's coming in, it is losing gravitational energy and acquiring kinetic energy, losing gravitational energy, acquiring kinetic energy, and it's going faster and faster. And pretty soon it's going faster radially than the speed of sound. And now you have a problem. If I have the Schwarzschild radius which has to bring it to rest, how could that happen? I can't bring a supersonic flow to rest unless I have a shock wave. So probably what happens is that I have a shock wave and I turn the supersonic flow through the maximum possible angle. And I turn it up or down, and it'll go out where the poles are. And I'll turn it and it'll become subsonic. And you would like to think that when it goes through that shock, it suddenly gets very, very hot, and you'll be able to see it. Well, that remains to be seen. But Jerry Oestreicher and I wrote a paper about that, that observation, that this flow coming in is a supersonic flow, and the only way you can slow it down is through an oblique shock. All right.
Excuse me, Gary.
Yes?
Does this figure mean that across normal shock wave, the flow doesn't change direction?
Across the normal shock wave, it doesn't change direction. It's still flowing. Theta is equal to 0 across a normal shock. But it goes from supersonic to subsonic. And that's what we talked about when I did the stationary shock and the flow coming in and going out. All right. So now, if you plot this figure, you'll find that M2, the Mach number, is less than 1 here, but it's greater than 1 here. So these are the small, where you turn the supersonic flow a small amount. So that's down here. And here's the normal shock here. And somewhere here, and there's a locus of the maximum turning angle, the maximum angle you can turn it for every M1. And it goes through here. I haven't quite drawn the line correctly because I didn't draw the figure very well. And this is the line, the locus of all points where the Mach number 2 is 1. Everywhere to the left, Mach number is 2 is greater than 1. It remains a supersonic flow. Here, it's a subsonic flow behind the shock.
Which tends to occur more
It depends how you design it. If you let me show you. I'll come to it. I'm about to answer your question. I won't forget it. So for the same theta going across here, there's either a large beta, which is near pi on 2, or a small one for any given m1. You could have this solution or this solution. So if beta is larger than beta of theta maximum, this is the locus of theta maximum, if beta is larger than theta maximum, it's called the strong solution, and the flow behind the shock wave is subsonic. For beta less, you're over here, less than beta of theta maximum, you're in the weak solution, and the flow is still supersonic behind that weak wave. You've just turned it a little bit, and that's the weak solution. All right. So now let's talk about some applications, and here's a very good one.
Gary, sorry to interrupt. So for these two types of solutions, strong solution and mixed solution,
Yes.
when you say the flow is supersonic after the oblique shock, do you mean the full velocity component or just
The full velocity component.
But the normal component would be subsonic?
The normal component has to be subsonic. Yes. But the actual velocity remains supersonic. So here's a very good example. The detached shock wave ahead of a bluff body. So this is the wing of the F-18 or the nose of the F-18. And here is the shock wave when it's flying supersonically. So right on the stagnation point here, the flow comes in, but it can't. We've already seen the only solution that's possible is when it's subsonic, because you only slow the fluid down by if it's subsonic with the diverging streamlines. So because of this stagnation point here, the streamlines have to diverge, but if it remains supersonic, the Mach number would go up, and that's not right. The Mach number can't go up. The Mach number has to go down. So there must be a normal shock. So right here, beta is pi on 2, and you have a normal shock wave. But now the shock wave gets weaker as you go further away here, because the flow doesn't have to remain normal to the shock wave. The shock wave gets weaker, so beta, it becomes less than pi on 2 as you move away. Here, the Mach number behind the shock is less than 1. And this is the line that I've drawn just imaginatively of where the Mach number is identically 1. And Mach number behind the flow is identically 1. And here, the flow is supersonic. And way out here, there will be a very much weaker wave to turn the flow. All right, so the bow shock includes all possible values of beta, and that's true whether the flow is 2D or axisymmetric. And this part in here is a difficult transonic problem because of the upstream influence for Mach number less than 1 here.
Excuse me, Gary.
Yes?
Can we know the distance between the shock wave and the object?
No, I don't know how to do it. And that's what I'm really saying. This is a difficult transonic problem. It's transonic. You've got regions here where Mach number is very close to 1, and it's very hard to solve. You can solve it numerically, of course. So that's why all these companies today have people who compute. They solve the equations for the flow over a helicopter on a computer before they cut metal. That I know. So now comes the answer to your question. Attached waves. Can we have attached waves? These are also very interesting. Let's suppose we had a 2D flow and we had supersonic flow coming in, and we want to turn the flow through an angle theta, and we want a flow out. And theta is now much less than theta maximum. And this is going to be a supersonic flow here. This is a fairly weak wave. Well, we could replace this streamline by a body. And that is what is done. So here's the body. Here is the nose of the missile in supersonic flow. And so we have what's called an attached shock right here. The flow's coming in. It's supersonic. We don't have any difficulty. This is a point, and the flow gets turned through an angle theta. So here's two cases. M1 is greater than 1, and here's beta, the angle of the shock with respect to the direction of the flow. And here M2 is greater than 1, and here we've turned the flow through an angle theta. Here is the case, another case where we had an even larger theta, and we had the strong solution, which depends on the boundary conditions, and now the Mach number is less than 1, and all hell breaks loose in here. Very difficult to actually solve it, solve the equations, because everything feels everything else. It's subsonic. Yes?
When we have supersonic flow going into it,
yes,
that's the overall supersonic flow, but does the normal component also have to be supersonic?
No.
It doesn't. Okay.
No, the normal component is always subsonic.
Before the shock?
No,
Okay.
after the shock. The normal component is always supersonic.
It needs to be before?
It needs to be. It needs to be before the shock. Otherwise, you won't have a shock.
Okay. So if can the flow still be supersonic even if the normal component is subsonic because of the tangential component?
No, you've got it wrong.
Okay.
The normal component is supersonic. Now, after the shock, the normal component is subsonic.
Yeah.
But the flow can be supersonic, yes.
Yeah. But can the same thing happen in the opposite way before the shock?
Let's go back to where I started this discussion.
If the normal component is subsonic, you would not get an oblique shock waveform.
Okay.
Yeah.
Okay.
So here's the figure. So you can see that this normal component is much smaller than this normal component. So this is the normal component, M1n, is supersonic.
Okay.
But I proved to you that out of it, even if this is 1 plus epsilon, this Mach number is 1 minus epsilon. I showed you that. That was important at the time. This velocity is always smaller than that. And so this flow has to be, because this is the same here as it is here, this angle has to be smaller than this angle here.
Yeah.
And that is the turning towards the shock.
Yeah.
And there's no change in the tangential component across a shock.
And there's no change in that tangential component. There can't be. If there were, control volume would all blow up, and you'd get the wrong answer. This wouldn't work. This wouldn't work. But it does work if the tangential velocity is the same. It's tangential to the shock. So I can add it. And you saw I added it to the energy, added it to the momentum, and it doesn't affect the mass. Okay.
Excuse me, guys.
Yes.
Sorry. You said, I don't know which lecture, but maybe 3 lectures behind. You said the maximum U2 of A2 for strong shock is 1.9, I think.
Ah,
So does this relate to this?
almost certainly.
How can we?
I haven't used that, but I mean, what I did was correct.
No, I mean.
Yeah, no.
How can you connect this idea to?
Well, it's a little subtle because now I'm talking about. I have to get myself in the right frame of reference, but I think this stationary shock. Now, what I did was the Mach number of the flow behind the shock with respect to the ground.
Now behind the shock is subsonic, right?
Yes. Yes. Normal. The normal component is.
No.
Yes. Okay, so I talked about detached bow shocks, attached waves, and the last thing
Hey, Gary, it's actually time to finish up, if that's okay.
Yes. All right. Well, I'll quit. Okay, I'll pick that up Monday. I quit. But you have to let me. I can't emphasize more the importance of you thinking as I'm talking. You must think as I talk. You must have a mental model in your mind or develop one. I can tell you that I've just seen something about that. Most of you here will know of Richard Feynman. Feynman came to a table at Caltech, and I was sitting there, and it was a table for people to randomly sit down at. And he came, and at the time I was advising the Minister for Defense here about the Strategic Defense Initiative. And Feynman came and sat down, and he said, or somebody said to him, "What do you think of the Strategic Defense Initiative?" And he said, "It'll never work." And since I had been advising the minister here, I knew a lot about it, and I had read The High Ground, which is Freeman Dyson's book called Weapons and Hope. And Feynman knew Freeman Dyson. I think he officiated at his wedding, I'm not sure. Anyway, I gave Freeman Dyson's argument for why it would work, and why SDI was a great idea. And anyway, the subject was dropped and we had lunch. But afterwards, Feynman came around to me and said that was very interesting. I said, yes, well, it's on account of my knowing something about it. He said, what are you doing here? I said, well, I've come back on a study leave. I've just been working on vortex breakdown for the F-18. Oh, he said. I said, you're interested in quantized vortices. Maybe you're interested in vortex breakdown. Yes, he said. I said, would you like to see how it goes? I said, I'd love to. So we walked back to my temporary office, and I worked it out for him on the blackboard. And here's what he said to me when I finished working it out. You mean the velocity helix unwinds the vorticity helix? It's incredible. It's incredible. He was not listening directly. I mean, he was following what I was doing, but at the same time, it's clear he had another model in his mind, which he was working through. He was working through. And that's what you must do. I'm not saying you're Feynman, but what you need to do is work through. You must develop the idea that you're here to learn. You're not here as blotting paper to soak up what I'm telling you. You are here to learn. And I'm only telling you things that, from my point of view, are A, interesting, and be helpful. So I've done a lot of things in this class. I've spent more time than has perhaps been done previously on some things because I think they're interesting and I think they're important. So that's why I've done it. Okay, so don't feel embarrassed about asking me anything. You can ask anything, and next week is the last